Bridge, please. So looks like the bridge is still muted. Shall we unmute the bridge?
The conference has been unmuted.
There we are.
I did that.
Yeah, I don't know why I kept pressing the unmute all and it wasn't having any impact.
Okay. Okay, any question? Any follow-up question or new question? So we do appreciate you asking questions through the questions box in live meeting, but this is one more opportunity for you to ask questions. Okay, now one person asked this question. Can you describe the PMI the same way? PMI. Now, I have a question for that person. Do you plan to be here in the antenna session or no? Do you want to attend the antenna session? Any plans for that? I just want to make sure that we use the time wisely. Okay. Everything is silent there. Okay, then probably we should wait. Okay. Okay, any other question? No one wants to take this opportunity? Would you let me have the exclusive right to use the bridge? You want to try it out? Any questions?
Okay.
This window of opportunity would not last for a long time. So go ahead, make my day. That was Clint Eastwood.
It was a good one.
Okay, any questions before we move forward? Yeah, I have observed that usually you like to ask questions using the live meeting questions box, but if you want to use the audio bridge, go ahead. I will start my 30-second timer. No question for 30 seconds. Then we move on with the traffic operations discussion. Twenty seconds. 10. Okay, so if you like to type in that's your call, so please continue doing that. So I will now mute the bridge.
The conference has been muted.
Okay, so very good. So let's then get back on to the traffic operations. Okay, but please continue submitting your questions. Okay, so we talked about three types of resource allocation: 0, 1, and 2. And those three types give the e-node scheduler a lot of flexibility. So that one decision the scheduler will make, that should I allocate type 0 or 1 or 2 to this specific UA. Another decision the scheduler will need to make is, should I have semi-persistent scheduling or non-persistent scheduling for this user. So let's take an example of this so-called non-persistent schedule. Okay, so we give some resource allocation, maybe resource blocks 0 and 1. We are giving 2 PRBs, and using those PRBs, the downlink shared channel is carrying data for this user. After some time, we give resource blocks maybe 3 and 4, maybe 3, 4, 5, 6 perhaps. And using those resource blocks, again, the downlink shared channel is carrying the traffic for the UA. So as you can see, we allocate the resources and those are used for data. Again, new set of packets would be going over perhaps another set of PRBs and so on. So the allocation that we give is valid for one subframe. Right? So if you want to give the user capability of getting data in future, you have to again allocate the resources. So the resources are given and they go away once the subframe is over. Now, if you have this kind of scheduling for non-persistent, the resources allocated do not persist, do not stay there for a long time. They are only for that subframe. Once the subframe is over, the resources disappear for that UA. Okay? So that's the non-persistent schedule. So the advantage here is that you can do adaptive modulation and coding. You can keep changing the resources. Right? However, the problem is that we have to keep indicating the resources. So it will consume more overhead. And that overhead is the control channel overhead. Because every time we need to send data to the user, we have to specify a set of resource blocks. So that will consume some overhead. Okay. Now, what other type do we have? The other type that we have is semi-persistent scheduling. The idea here is that the resources that we give stay with the user for a long time. So this is suitable for the applications such as voice or IP, where you know that you will use on average, let's say 10 kilobits per second. So you allocate the resources once, the UA will continue using those resources until the eNode B changes its mind, okay, and does something else. So until specified otherwise, the resources are there for the UA to use. So we are no longer using the control channel overhead all the time. We use the control channel once to give the allocation, and then that allocation will be valid not only for one subframe but for many, many subframes to come. So let's see how to do that for voice or IP. Okay. We are giving the semi-persistent downlink allocation here. Okay. So the green color is your downlink allocation, okay, but it is semi-persistent. Semi-persistent. Then we send this packet. This blue color is your actual voice or IP packet. So we are sending that packet. This time, our packet is successfully decoded by the UE. So the UE is sending the acknowledgement, positive acknowledgement. Packet is okay, no problem. After some time, we have another voice or IP packet. So as you can see, we did not have to specify the allocation again. So whatever allocation we have, it is also valid here. Now this time what happened? That we could not decode the packet correctly. So there is no positive acknowledgement going to the E node bin. So now E node bin is to retransmit the packet. And for retransmission, we have to specify the allocation, and that's what we are doing here. So this is retransmission allocation for retransmission. And using that allocation, we are retransmitting the packet. So this time we are okay. We are sending positive acknowledgement to the E node bin. Again, another voice over IP packet. We did not indicate any resources for that because we still have the semi-persistent allocation. So for the new transmissions of packets, our semi-persistent is valid. We don't need to re-specify that. We need to allocate resources for retransmission. But for the new transmission, we already got our resources allocated by the first semi-persistent allocation. Okay, so we keep doing that, and now after some time, we enter the silence interval. Okay. So if I'm talking to my wife, there is a long period of silence. My vocoder doesn't need to generate any bits. Because she is talking, I am listening. So that's silence interval. My battery power, that's why is lasting for a very, very long time. No need to talk much. So during the silence interval, what will happen? We do not need to use resources. So if we do not use resources, okay, for certain time period, then there will be implicit release of the allocation. So the resources that we got allocated, now they are gone with the wind. Now what else? Well, after some time, we'll again have speech on time. And whenever we are ready to do the activity again, we will just allocate our new semi-persistent allocation, and then the overall process will be repeated. So in summary, our semi-persistent scheduling will last for a long time. However, the non-persistent scheduling, every subframe we need to allocate. That, I'm giving you one resource block. After some time, I'm giving you 3 resource blocks. So we have to keep allocating the resources whenever we want to do data tasks. So those are the 2 types of scheduling, semi-persistent and non-persistent. So for voice over IP type applications, where we know that the data rate would be quite consistent for speech, let's say 12.2 kbps for AMR speech, and for EVRC 8 kbps EVR6. So we have a pretty good idea about the data rate. So it's possible to do semi-persistent scheduling in that case. Oh, look, we have a question. Okay, so after how much silence do we release the resource? Okay, now in this specific example, I'm just picking surveys such as voice over IP. Now, in general, how much time period needs to elapse before the resource release? That would be defined in the standard. So we can configure the UE through RRC signaling, and as part of the configuration, we can tell the UE that this allocation, let's say semi-persistent allocation, will be valid for a long time, and there will be implicit release if we have no activity for, let's say, 20 subframes. So the 20 subframe type number will be conveyed to the UE by E node B. So normally that's how we configure the parameters. We tell the UE through RRC signaling various parameters that we should use. So silence type interval will also be specified through RRC signals. Anytime you want more information, just send your question. And please maximize the use of questions box. And is there any difference between semi-static and semi-persistent? Static. Maybe, that may be another way of saying the same thing. The first one, this one, let's say, this is also called dynamic schedule. Maybe we didn't. Okay, so some people will call this dynamic because every subframe you can change the allocation, right? And you can think of this like semi-static. Yeah, so that would be another way of saying the same thing. Yeah. But the standard uses the term semi-persistent. But yeah, I would think that semi-static would mean the same thing. However, it is not a standard specified term, semi-static. Semi-persistence is the term used in the standard. Thanks for the question. So we looked at two specific topics. We looked at the type 012 resource allocation and then semi-persistent versus non-persistent schedule. One more topic that is under the responsibility of the eNode B scheduler is how to form a package. So we need to decide as a scheduler what transmission mode should I use for this user. And there are several transmission modes available. We can choose just to send data on one antenna. Maybe I will do transmit diversity. The CQ value is low and the rank indication is just 1, meaning there is no hook or MIMO type technique. So we can use the feedback coming from the UE while making a decision about specific type of transmission mode. Also, we need to decide that for that user, should I do new transmission or should I do retransmission? Normally, we would give priority to the retransmission. That's the normal way, unless, of course, we have some high priority voice or IP type services and retransmission for web browsing. So maybe we can have some additional delay because we do not worry too much about the web browsing type delays. Okay. So, but in general, the retransmissions would get higher priority. How many bits should I send out to the user? So the size of the transport block is also some number, right, that we need to figure out as the eNode B. Now, the transport block size basically that is given by map layer to the physical layer. This is the transport block. And during a subframe, which is 1 millisecond long, our eNode B will send one or two transport blocks, one or two. Okay, and modulation scheme, of course, we know that we have 3 schemes available: QPSK, 16 QAM, and 64 QAM. And how many resource blocks for a given user? Also, we need to decide. The most important feedback is CQI because that will dictate what kind of modulation we can choose, how much coding we need to provide, and so on. TBS is the transport block size. This is the modulation and coding scheme. Coding scheme actually is just the turbo coding, but how much redundancy we want to put, that will depend on the CQI value. So as you can see, our eNode B scheduler is making a lot of decisions, right? Very, very important piece of software. Time for a question. So our target is 100%. So let's see how close we get to that target. I will give you a minute to think about this. Think and click. And please participate in the poll. Let me give you 30 more seconds. And in the meantime, we'll answer this question. Yes, the transport block defined at the MAC layer and mapped to the resource block physical. Yes, that is correct. That is correct. MAC layer will give one or two transport blocks to the physical layer, and then those bits will pass through various processing blocks at the physical layer. For example, we will add CRC, then do the turbo coding, maybe some sort of redundancy in terms of repetition. We may need to do modulation, then IFFT, all those. But when we do the IFFT, we need to pick the subcarriers where those bits should be going. So yes, physical layer will map those bits eventually to the specific resource block. That is correct. Okay, let's see what we have here. We have 93% correct answers. MCS is yes, modulation and coding scheme. Absolutely perfect. So we support both the semi-persistent and the non-persistent. We support both. That is true. In WiMAX, we have support only for non-persistent. Okay. So that's why WiMAX is less efficient as of now for real-time services such as voice over IP, because it will consume a lot of overhead and that will make it less efficient. So voice over IP capacity of LT should be better than that for WiMAX. We have one more question. What is RV for retransmission? It's not a recreation vehicle, of course. Then what is it? This is redundancy version. Okay, let me give you a 1 minute view of redundancy. Okay, so basically we are doing turbo coding. Let's say 1000 bits. Rate 1/3. So we have some parity bits. These are systematic bits. Same as original information. Okay. Let's say I have space for 1500 bits. That's how much space I have for my data transmission. Okay. So I will say, okay, I will use redundancy version 0, and that means I will prioritize systematic bits, meaning I will first fill up the packet with, fill up the space with all the systematic bits, 1000. Then I still have 500 bits worth space left. So okay, I will put 250 from here, and then I will put 250 parity 2 bits. Another example would be redundancy version, let's say 2, and these are examples. Okay. So this would be close to the truth, but I'm making this, the number 2, I'm making this up, but this is the meaning for redundancy version 0, that we are prioritizing systematic bits. Okay, redundancy version 2 may mean that I am prioritizing non-systematic bits. So you can look at the standard and find the exact meaning of number 2, but here it is an example. I'm just covering my backside so that you do not come up to me. Prioritize redundant or parity bits. Okay, so I have this case, so I will put 750 from, maybe I should continue using the same color. So from here I put 750. So in this case I have no systematic bits at all. I'm filling up the packet with redundant or parity bits. So in LT we support this kind of redundancy versions, and you can look at the spec and get the exact meaning. But redundancy version 0 will correspond to prioritization of original information. It is up to the e-node scheduler what it wants to use for retransmission. The first time we transmit, we will send out RV0, but for all other retransmission, completely up to the e-node scheduler, whether it wants to stick to RV0 all the time or it wants to keep changing. Thanks for your questions. Keep your questions coming my way. Okay. And no limits on the number of questions that you can ask. Okay. Very good. So we talked about that. Okay, so what happened so far? Our UE sent out feedback, CQI, PMI, then e-node B executed scheduling algorithm. And now step number 3. We need to convey to the user what resources we are giving to the user, and then we have to transmit data using those resources. That is the next topic. So downlink control channel, that is the channel that is of interest to us. And there are several formats. So here I am giving you some examples. Okay, standard has more formats defined, but I just want to convey to you some examples. So let's say DCI format 1. So it could give you type 0 allocation or type 1. Right? There are 3 types, 0, 1, and 2. And that is only for one code word. So if we are doing, let's say, non-MIMO transmission, then you can use format 1. We will indicate the resource blocks for that specific UE, what kind of modulation coding scheme, what kind of redundancy version, and so on. If you want to do MIMO type transmission, then we will use type 2. DCI format too, and that would indicate parameters for MIMO or spatial multiplexing. So we can specify what kind of pre-coding we are doing, and again modulation coding scheme, redundancy version, and so on. So basically, the control channel should specify all the parameters to the UE, and using those parameters, our UE will retrieve the packet from the high-speed channel. And if you are wondering what is this so-called code word, it is nothing but whatever comes out of turbo coding and then rate matching. Rate matching, we may be doing some sort of repetition. Sometimes we have more code symbols generated and we have to get rid of some of those puncturing. So that's nothing but essentially output of the turbo coding block. But we may not be able to send all those symbols, so we may have to do puncturing and things like that. So that's your code word. Whatever comes out of the coding block is essentially your code word. Okay, so in summary, there are different formats of DCI, downlink control information, and they will convey different types of allocation, maybe for just non-MIMO transmission, for type 0, 1 versus type 2, etc. We have conveyed to the UE all the parameters for downlink transmission. So now very easy for the UE to retrieve data from the allocated resource blocks, and that is of course OFDMA based reception. The control channel has already told us and what resource block we are supposed to use, what is the modulation scheme being used, is the base station using one antenna transmission or multi-antenna. All those things are already specified by the control channel. Okay. Now, finally, so in the previous step, basically we send out a packet to the user. So the final step is to let the base station know whether we successfully decoded the packet or not, take or make. So that information is going in the uplink, okay? And that is nothing but hybrid ARQ. For the downlink transmission, we have so-called asynchronous retransmission. Let me just quickly review asynchronous retransmission. So basically, we are sending packet P from A node B, and then the UE sends out negative acknowledgement. The way it says, no problem, I will retransmit. Some problem, again, negative acknowledgement. Then base station is now retransmitting packet. So as you can see, the timing between successive retransmissions is not fixed. Sometimes we have shorter time interval between two retransmissions. Sometimes we have longer time. It is completely up to the A node B schedule. That's why we call it asynchronous. So for the downlink, A node B always does the retransmission. And the benefit of this is it gives the base station scheduler more flexibility. So if the base station scheduler is busy with other high priority users or high priority applications, then we can wait for additional time period. Okay, for our email, web browsing, we are not too much worried about few milliseconds of delay here and there, right? But for some voice or IP users, if you do not serve them quickly, then they will have poor perception of the service. So this kind of asynchronous hybrid IRQ will give the eNode we schedule a lot of flexibility in scheduling the retransmission. Okay, and by the way, in 1xc video, we always have synchronous hybrid IRQ in both uplink and downlink, forward and reverse. There is always a fixed time delay between retransmissions, either the base station or the access terminal, always synchronous in 1xc video. And that specific ACK or NAC can of course go over the control channel or the shared channel, the traffic channel. The delay between reception of the packet and ACK/NAC, that is always fixed 4 subframes. So in that previous picture here, this time interval here, four milliseconds. So once the UE gets a packet, after 4 subframes, the UE will send out positive or negative acknowledgement. Okay. Anything else? Yeah, other things are okay. We know all about the downlink transmission. Now let's take care of uplink data transmission. Okay, here is the basic idea. The UE may send a scheduling request on the uplink control channel, or it may just do the random access. But in any case, whenever one of these two things happens, then eNode B knows that this UE wants to do some uplink data transmission. So it will give little bit of bandwidth for uplink transmission. And of course, we will specify such a grant by using the physical downlink control channel and specifically DCI format 0. 0 is for the uplink allocation. So as a UE, we got little bit of bandwidth. Using that little bit of tiny bandwidth, the UE sends out buffer status report. Okay. And that will tell us, for example, that okay, we have 1 megabytes of data waiting in the buffer. So here is the buffer that we have at the UE, and we have a lot of data. So we'll indicate that, oh, a lot of data that we need to send. And of course, along with the buffer status report, if we have some data, we can also start sending that out. So eNode B now knows that this user had a lot of data. So let me allocate adequate resources. So maybe earlier I got maybe 1 resource block allocated, but now maybe I will give 5 resource blocks. Okay. Again, the control channel DCI format 0 will indicate the set of resources we are giving to the UE for uplink. And now using those 5 resource blocks, we are sending data, and along with the data, of course, we will send buffer status report. Whenever we use dedicated channel in the uplink, For our traffic, we are using so-called physical uplink shared channel. So that is your traffic channel. Do you remember the maximum data rate on uplink shared channel? How many megabits per second? Who remembers? Is your memory still with you, or it has gone somewhere else? How many megabits per second uplink? That is what is the maximum peak data rate we could support? How many megabits per second? 25 for 10. Okay, I got a couple of answers. Okay, so the maximum we can ever get is 75. It's close to 75 megabits per second. But of course, that assumes that we have 20 megahertz spectrum. Okay. And we have category 5 device. Okay. And that device can support 64 QAM modulation scheme. So if you have 10 megahertz, then the data will be half, okay, because we have the spectrum, and you can adjust that for modulation scheme if it is not category 5 but some other lower category terminal. Okay, thanks for attempting to answer the question. Okay, so that's the high level view of the basic steps of uplink data transmission. Now we will take a closer look at all these steps one by one. Okay. So one of the ways in which we can make a request for uplink resources is by sending scheduling request. So we can send an uplink control channel. So format 1 of uplink control channel. Basically, the only thing we send is scheduling request, nothing else. Actually, this is just present or absent. That's it. So either a bit is present or there is no scheduling request, meaning the bit is absent. That is format 1, as simple as that. So our eNode B is looking at the uplink control channel, and if it doesn't detect anything, it means that this user does not want to make any uplink scheduling request. However, if eNode B detects a bit on the uplink control channel format 1, then it knows that, oh, this UE wants to make a request for uplink resources. So this is one format. Another format allows the UE to send out scheduling request along with the hybrid ARQ name. But of course, this is to support downlink transmission. So in that case, we can use these formats 1, 1A, 1B. These are the 3 formats that are available for the UE to send out uplink control. But in any case, as far as uplink data transmission is concerned, we are more focused on the scheduling request. So we can send that using any of these formats. So scheduling request itself will go over the uplink control channel. But if we have no channel at all, then we can just start sending the random access preamble, and that is an indirect indication to the eNode B that maybe this user wants to do some data transfer. So whenever some data arrives, we send some scheduling request, but now no response. Then we can send another scheduling request, and so after some time, now the base station is responding to our request. we are using DCI format 0. That is the format for uplink allocation. Other DCI formats, format 1, 2, etc. for downlink resource allocation. But format 0 of DCI is for the uplink. So we give tiny bandwidth. And now we will use the current, the tiny bandwidth, to send this buffer status report. That is said to go over the uplink shared channel, physical uplink shared channel. In node B, we'll take a look at the report, and it could choose to give semi-persistent or non-persistent grant. Okay. So it is again up to the node B scheduler what kind of scheduling it wants to do for the uplink transmission. So let's say we do non-persistent scheduling. So whenever we get resources allocated, we will use those resources to send out data on the uplink shared channel. So in summary, scheduling request is just helping the node B figure out that, oh, this UE wants to do some uplink data transfer. Now, how do those buffer status reports look like? Basically, we have short report in just 8 bits. Okay. One field here indicates the logical channel group ID. Okay. And that will say how much data we have in the buffer. So our standard has some kind of table. Let's say if it is 00001, it means we have X bytes, 000, maybe 10 or whatever, maybe we have Y bytes and so on. So how much data we have in the buffer would be indicated by a set of 6 bits. And the data corresponds to which specific logical channel group ID. So for example, if we are doing video streaming, then that would be maybe part of one logical channel group, let's say number 0. Email, for example, little bit lower priority, maybe that is logical channel group 1, and so on. So we need to inform the scheduler what is the logical channel group ID for which we are reporting the buffer size. The node we can look at this report and figure out that, oh, this logical channel group ID is a high priority service, maybe voice or IP video streaming, so it will immediately allocate resources. On the other hand, if it is like email type low priority logical channel groups, then it could decide to wait a little longer. But essentially, we need some way of informing the scheduler how much data we have. So that will dictate how many resource blocks the node scheduler should allocate to the UE. Because there is no point in getting 50 resource blocks, but we have very little data. Right? We do not want to send zeros using those lots and lots of resource blocks. So this is one kind of report, short report. We also have long report. So we support the 4 logical channel groups. So we can report buffer size for 4 different groups. And maybe one group corresponds to email, another group web browsing application, and so on. So this is little more comprehensive report. Could be short report, could be long report. Here is an example of the types of buffer status reports that we can send. One kind of report is the regular buffer status report. In that report, we have empty buffer, and now new data comes. Or maybe we just moved to a new cell. So this is now handover. So as far as the new cell is concerned, right, it is like a brand new data transfer with that specific cell. So our UE will then send regular buffer status report. The eNode B can configure the UE to send periodic buffer status reports. So through RRC signaling, we can tell the UE that keep sending me buffer status reports maybe every 100 milliseconds or every 20 milliseconds. We can pick these kind of numbers. So with that periodicity, the UE will be sending our buffer status reports. Yet another kind is so-called pairing buffer status report. Okay, so let's see what pairing is all about. The main reason that we have this is to use the available resources efficiently. Okay, so let's take an example. Let's say in the past we gave 10 resource blocks. Okay, so now we are sending a packet P. Now, because of the buffer, because of some past buffer status report and so on, we had been given 10 resource blocks. Okay, so those are the resources that we are using to send out packet P. Now, we do not have a lot of bits to send. So what happened is we consumed up to this much space. Let's say I could have sent out X bits, but I'm sending fewer than that. And then the remaining one, I will have to put some zeros. Okay. And here is the buffer status report. So my buffer status report, right, I'm sending, and still there are a lot of zeros, still zeros. So whenever we have too many zeros to fill up the packet, we will send pairing buffer status report. Because normally we want to send out buffer status report along with the traffic, and we just hope that that will avoid the need for any zero padding. However, now even after we put in the buffer status report, still there is significant space left. So whenever this kind of situation arises, then we send this kind of pairing buffer status report, and our eNode B will know that, oh, there is 10 resource block, too many. The user doesn't have enough data for that, so it will next time around will give maybe 7 resource blocks and so on. So hopefully now we are able to fill up the blocks with the bits, so we do not have too much waste of our resources. So in summary, this will help us allocate resources, and we will use those resources efficiently. PTI stands for buffer status. We have a question. So let's see where is the PTI? Oh, PTI. transmit time interval okay, in LTE, how fast can we change the data rate? How fast? Every what? Every something we can potentially change the data. Every 1 millisecond. Very good. Perfect. Perfect. So that is your TTI. 1 millisecond subframe is our TTI. Thank you for your answer. 1 millisecond subframe. Oh, we got one more answer. Oh, super. Keep your questions coming. Okay. So those are the three kinds of buffer status reports. In summary, scheduling request, just one bit that tells us that, oh, UE has something to send in the place. And buffer status report gives the eNodeB even better view of the resource requirements because we indicate how many bytes we have in the buffer. So that will tell the eNodeB that, okay, do we need to give just a couple of resource blocks or do we need to allocate a lot of resource blocks to the UE? So eNodeB's scheduling algorithm gets a lot of help from this kind of reports. Okay, let's get this question answered. I will give you a couple of minutes. Think and click. Oh, and this is true false. 50% chance of getting this right. That is, if you are generating a random number, tossing a coin. But hopefully that is not the case, and you have been awake all the way so far. So hopefully we should get close to 100% accuracy this time. Okay, and just to make sure that you are understanding the question right, can we use the control channel to specify the downlink allocation? Can we use the control channel, the same control for uplink allocation? Or do we have some other kind of channel to convey the uplink allocation? The intent here is, what kind of channel do we use to specify downlink allocation, to specify uplink allocation? So do we have so-called physical downlink control channel for downlink allocation and uplink, or we have some other channel for uplink allocation? That is the question. Yeah, I think maybe we are not interpreting the question in the same way. So, okay, what I mean here. Okay, let me tell you what I have. So we have 50-50. So let me ask you another question. Okay. So, okay. Resource allocation. Yeah, maybe there is some potential misunderstanding. Resource allocation. So I am the eNodeB, okay, and I want to specify to the user downlink resource. Okay. So Okay, let me ask you this question. Okay, E node B wants to specify downlink resource allocation. For example, that physical resource blocks 0, 1, 2, and 3 for downlink transmission. We want to provide this kind of allocation to the user. Which of these channels will I use? Physical downlink control channel, physical broadcast channel, physical downlink share channel, physical uplink control channel. A, B, C, or D? To do this, A, B, C, or D? Oh, you do not see the whiteboard. Oh, sorry. Let me then go back here. Yeah, sorry about that. Oh, okay. Yes. Okay. Thanks for staying awake and responding to me quickly. Okay. So I want to convey the downlink resource allocation. I want to give resource block, let's say 0, 1, 2, and 3. So which of these options is the correct one? A, B, C, or D to convey the downlink allocation? So feel free to type in your answer, A, B, C, or D. Okay, question. Okay, so I got several answers. Okay, so I got A as the answer. Okay, good. Okay, so to convey the allocation, we will use physical downlink control channel, and that is at the front of sub. Okay, here physical downlink control channel will exist in initial portion of the subframe. Okay, now let me ask you another question. We want to convey to the user uplink resource allocation. So maybe I want to give physical resource blocks 0, 1 all the way up to maybe 21. Let's see. To specify the uplink resource allocation, which of these 4 channels will I use? A, B, C, or D? To specify. Okay. Yeah. Okay. I will wait for 5 more seconds. So far I have 2 for this and 2 answers here. Ha. Oh, okay. Let me repeat the question. Okay. To convey the uplink resources to the user. Basically, as E node B, I want to convey to the user that I want to give you many resource blocks, 0 all the way up to 21. Okay. So to convey this kind of resource allocation, which channel will I use? To convey the physical resources for uplink transmission, which channel will I use? Okay, so let me see. 1, 2. Okay, so far I have 2 for this, and now this number has increased. 1, 2, 3, 4, 5. 5 answers for that. Okay, this is the correct answer. Again, I will use the downlink control channel. See, the name is a little bit misleading. It's a downlink control channel. But even though it is so-called downlink control channel, one of the formats, DCI format 0, that will specify uplink resources. So now some of you chose this option, right? Uplink control channel. Now let's see what could potentially be on the uplink control channel. So when the UE sends uplink control channel, it can send information such as scheduling request, hybrid ARQ ACMAC in response to the downlink data transmission, then feedback such as PQI, range indication, pre-coding matrix indication, and so on. So these are the kinds of things that we send on the uplink control channel. Since it is an uplink channel, we cannot just allocate it some resources, right? In OFDMA systems, who is in charge? The base station is in charge. Our E node B is very, very fast. It is making all kinds of decisions. So the uplink resources and the downlink resources, both are specified to the UE by E node B. So we need a downlink channel to specify that. And the name of the downlink channel is PDCCH, Physical Downlink Control Channel. So that will convey the downlink resources, that will convey the uplink resources. So hopefully now it is more clear than before. Okay. And we'll take a short break soon, and when we unmute the bridge, feel free to ask additional questions, okay, if you want to use the audio. So if you want, we can have further discussion on that topic. Okay. Oh yeah, see, the reason that I thought that you guys had problems answering the question, let me tell you why I went through the whiteboard here. Because the thing is, when I have this physical downlink control channel area, let's say this is that area. So inside there, let's say I have this control channel, another control channel, another control channel, another control channel. Okay. So these are individual control channels. This is control channel 1, control channel 2, control channel 3. So this may carry, let's say, downlink allocation for UE1. This would carry uplink allocation for UE1. I'm just giving some examples. Okay, downlink for UE3, etc. So a given control channel can allocate only uplink resource or downlink resource. Okay, but not two exactly on the same control channel. So I thought maybe that's why you guys were confused that whether we should have true or false. So that's why I had to explain. But the correct answer is yes. It is true that the control channel can convey the downlink allocation and the control channel can convey the uplink allocation. So the correct answer is true. Oh, we have some. Someone has changed the color of the seat. Okay. Okay. Let me unmute the bridge so that we can take care of that question.
The conference has been unmuted.
Yeah. So it looks like someone has a question. Oh, it's now proceed. Oh, okay. I thought. Okay. Someone wanted to ask a question. Oh, here is the question. Okay, so physical. Okay, let me mute that in that.
The conference has been muted.
Okay, a physical. Oh, I see. Okay, it is physical downlink control channel. So PDCCH stands for physical downlink control channel. If our list of acronym says otherwise, sorry about that. Okay, so it is physical downlink control channel. So the correct answer here is true. The control channel conveys the downlink allocation and the control channel carries uplink allocation. Okay. Okay, so what happened? Our UE sent out scheduling request and maybe even the buffer status report. And now E node B will execute scheduling algorithm. So of course we need to consider the scheduling request coming from the UEs. We also need to, of course, look at how much data the UE has in the buffer. What is the priority of the logical channel that are part of the logical channel group? And what is the quality of service that we need to meet? Because remember, we have all these EPS barrel and we control the QoS at the barrel level. So if it's voice or IP bearer, we have one kind of QoS, email bearer, another QoS level, and so on. So we need to make sure that the allocated resources can meet the required quality of service. So we consider all these various factors and we need to come up with the scheduling graph. And this is nothing but the allocated uplink resources. Okay. Just like the downlink, uplink also has two types of schedule. We have non-persistent scheduling. So basically, let's say, okay, so in the past, we had given some allocation to the user, and the user is sending out the regular data, and along with the data we have buffer status report. Now this would say, oh, I have a lot of data now, right? Because we have perhaps a new set of bits that we got from the application, and the base station will allocate resources so that we can send out the data in reasonable time frame. So again, we use the grant and send data, another grant, again data. So whenever we get the resources, they are valid for one subframe. And once the subframe is over, our resource allocation is also gone. Okay. So this is just like the downlink, nothing new. So validity of the allocation, just one subframe. Semi-persistent, just like what we discussed earlier. Right? We have the same idea here. We allocate the semi-persistent allocation, and using that, the user will be sending out application packets, let's say voice or IP packets in this case. And whenever we want to send out some silence descriptor, we are entering the silence time interval. And in that case, we need to encode noise, the background noise. That will require dynamic schedule. But other than that, it is similar to what we have seen. For the new allocation, okay, we have to rely upon the dynamic portion of the scheduling, the non-persistent. And for the semi-persistent, we can continue using the previously allocated resource as long as there is no silence. But other than that, it is similar to what we have seen for the downlink. The actual data will go over uplink shared channel. Again, all the parameters that we are supposed to use, they are already conveyed to the UE by the control channel, physical downlink control channel. So for example, base station tells us the UE which resource block it is supposed to use, whether the frequency hopping is turned on or off, what kind of redundancy version we are supposed to use. You can override the previous hybrid IQ parameter. Maybe the UE will try 3-4 times to retransfer the packet, but if the E node B wants, it can always ask the UE to start from scratch again. Modulation coding scheme, again responsibility of the E node B. So all the parameters are specified by E node B. So the UE just follows the orders of E node B. And of course we can always do adaptive modulation coding, because the E node B can always look at the reference signal that is accompanying the uplink shared channel, and based on the channel conditions on that one, and also we can request the UE to send sounding reference signal. So we can use the reference signal, so-called demodulation reference signal, and sounding reference signal. We can use the help of those two types of reference signals to figure out what kind of modulation coding scheme we should use, and which portion of the spectrum should be allocated to the UE for uplink transmission. Okay, so we send a packet to the user, to the E node B in the uplink, let's say packet Q. Then E node B will have to respond with positive or negative acknowledgement. So that's what we are focusing on here. For the uplink, we have synchronous retransmission. So if we go back to our discussion of the hybrid IQ retransmission here, then for the downlink, we indicated that the E node B can retransmit the packet anytime. So the time between two successive retransmissions is not fixed, it is variable. However, the uplink is a different story. In the uplink, we have synchronous hybrid IQ. So here is the UE transmission. Let's say we sent packet Q, and the E node B sends out negative acknowledgement. Then we will have retransmission of Q. Again, some problem. Negative acknowledgement, and so on. Okay. So basically, as far as the uplink is concerned, we will have fixed time interval between successive retransmissions, and of course, between the reception of a packet and sending of ATNET, we have 4 subframes delay. So basically, after UE sends out a packet, E node B will send the ATNET 4 milliseconds later, and the UE has to retransmit exactly 8 milliseconds based on this diagram. Okay. So downlink we have asynchronous hybrid IQ, uplink we have the synchronous hybrid IQ. And the advantage here is the simplicity of implementation. Less overhead. Because we do not need to tell the E node B right? Whether this is like a new packet or this is retransmission. Right? It is already predetermined, just like one exhibit. Okay, so let's get back to our slide. A total of 8 hybrid RQ processes. Okay, this process is same as interlace in one exhibit U. Okay. And if you are familiar with UMTS, UMTS uses the hybrid RQ process for HSDP and HSUP. So basically, okay, who would tell me the motivation behind process? Okay, let me ask you another question. If I had just one hybrid RQ process, not 8, but only one process, what would be the problem with that? Let's say we have defined only one hybrid RQ process. Do you imagine any problem, or everything will be just fine? Any potential drawback of having just one hybrid RQ process as opposed to 8? Okay, let me unmute.
The conference has been unmuted.
Okay, who would like to give me the answer using the bridge, perhaps, if you do not want to type in too much? What is the problem? Is there any problem? One answer that I got is one application at a time. Not exactly, but you need to think a little further. Any problem if we had only one process? Or if you have one exhibitor background, then what would have happened if we had only one interlace in one exhibitor? Any problem? No problem? Or we just do not want to express our opinion? Okay. Let me mute. Okay.
The conference has been muted.
Okay. So the basic idea behind the processes is we want to increase the throughput. Increase throughput. Why? How? Let's say I had only one process. Okay? Just one process. So here's the situation. I have some packets, P, Q, R, S, etc. And we can take downlink or uplink example. Oh, we were one answer that I got, early termination. We can do that even with one process. But let's discuss this and you will know why. Okay, we have one process and this is that process. Process number 0. So this process will pick a packet P. Okay, and then it will transmit that packet to the user. Now, since sorry, again okay, yeah, sorry about that. I need to share the journal. Sorry about that. Okay, but thanks for your very quick hybrid RQ negative acknowledgement. So when you send me neg, I can quickly react. Okay, so that's my implementation of hybrid RQ. Okay, so we send a packet P. Now, this process cannot send anything else until it gets back the response from the UE. Because if it is positive acknowledgement, it will pick a new packet. If it's a negative acknowledgement, then it will retransmit old packet. Only when there is a positive acknowledgement, it will send new packet queue. So as you can see, if you had only one process, that poor process has to wait for egg or neck before it can figure out what to do next. Should I send a new packet or should I retransmit? So we have to wait. It means that if I send packet P here, then I have to wait for egg or neck, and after that I will do maybe retransmission or new transmission. So what is happening during this time period? Idle time. If there is idle time, we are potentially wasting the resources. Maybe there are not that many users, maybe one or two users in the cell or sector. So we are not using our system resources for this time duration. And we want to do better than that. So we said, okay, let's have multiple processes. So this is like having multiple interlaces in one XC video. Okay. In DO we have 4 interlaces. So here we have 8 processes. So what will happen is I have one process number 0, process number 1. I will just give you a couple of process examples here. So now I have some packets lying in the bucket, lying in the buffer, packet P, Q, R, S, and whatnot. Okay. Now all these processes, they run independently. One has nothing to do with another. So process 0, okay. So it picks a packet P. So process 0 has only one goal in life. I need to send out packet P. That's it. It doesn't worry about anything else in the world. So it will send out packet P. Okay. Process 1 says, oh, I have nothing else to do. What do I do? Let me pick a packet Q. Let me send packet Q. And then I will wait for egg or neck. Process 2 says, oh, what should I do? Let me get a packet. So now those processes are waiting for their own egg or neck. So if we have enough numbers of processes, we can keep filling up the pipe. S, T, U, V, and whatnot. So 1, 2, 3, 4, 5, 6, 7, 8. We have 8 processes. And now, by this time, we would have received, let's say, X for packet P. Okay, so we are process 0. We are waiting for X on X. Oh, we got X. It means I can go ahead and send a new packet. So new packet now from process number 0. So let's say packet A. Now these after some time, let's say we get negative acknowledgement for packet Q. So our process Q has got neck. It says, okay, no problem. I will retransmit packet Q, and so on. Since we have multiple processes, right, we can keep filling up the pipe. Each process takes care of its own packet. No need to worry. So we can increase the throughput. So we have no idle time, and we can keep filling out the pipe of our canal. Eight processes with individual XNext TCP window in. Yes, you can think like that. That is correct. So conceptually, it is like TCP window. That is correct with individual access. Correct. Conceptually, it will work that way, yes. In practice, when you're doing web browsing, right, you just have one TCP connection with at a given time with some web servers, and one web page could be divided into many IP packets, and we can send chunks of those IP packets using many processes. But conceptually, yes, it is like that. Okay, so hopefully we have now a good understanding of this so-called process. Okay. And the channel that we use in the downlink to send the hybrid ARQ connect is physical hybrid ARQ indication channel, and just like the downlink, we have 4 subframe delay between the transmission of packet and transmission of hybrid ARQ. How many retransmissions should the UE do? But that would be completely up to the scheduler. It will tell the UE as part of the RRC signal that okay, try maybe 4 retransmissions, and that's it. Then we will rely upon upper layers to do the retransmissions if we so desire. Okay, let's have a poll. And once we are done with this, I will give you a short break. Okay. So let's aim for maybe 3 minutes. So we discussed both asynchronous and synchronous times, right? So is it true? Downlink asynchronous, uplink synchronous. Okay. Let's wait for 30 more seconds. Okay, very good. We got little over 80% correct answers. Very good. So it is true that downlink has asynchronous retransmission, uplink synchronous. Okay, it's time for a 10-minute break, and once we come back, you will have an opportunity to use the audio bridge. Let's see if we have any person who takes my offer. Okay, so 10 minutes.